Welcome back on the introduction to ML and AI using Python for mechanical aspirants. So to continue with the session, as I told, we had this final project, predict the output by using all supervised learning machine learning algorithm and identify the differences in the results obtained using this algorithm. So what you have to do, as I already told, you can use a user-defined function and you can predict using all the different supervised machine learning algorithm for the classification. Once you get the data, you will come to know, and then over there you have to implement all this machine learning algorithms. Okay, and then you have to see which algorithm is performing better, and that would be great if you can identify the reason behind that. Okay, and then second would be quite complicated. As I told, it's performing the clustering for the same data and then use predictive algorithms and identify the differences obtained in the results in performing prediction with and without clustering. So what I meant is, in this case, so you would be having the data x1, x2, x3 and so on. I'm not sure how many x, and then y. Okay, so first you have to consider that there is no y in this case. Okay, and then implement your clustering. After clustering, you will come to know, based on this y, you would be knowing that how many outputs should be there. For example, if this y has 3 outputs, then try to divide this into 3 clustering techniques. Okay, try to divide this using any clustering techniques into 3 clusters, and then what y you will be getting, make that as a new column as a cluster one, that this record goes under which cluster, this record goes under this cluster, and based on this cluster try to predict. Now you can consider this as your y output, you can consider this as your y output and then do predictive modeling. That's a one way, and then the other way is use this as your y output like in a second method, and then implement predictive modeling or like classifiers. Whether it's a, I think it would be a classifier model, so implement classifier on that. Okay, so now you got my point, right? You have to perform the same thing 2 times. One, by considering this given output in the data set. Second, do not consider this as an output and just do a clustering technique, and you should take the value, the number of clusters should be same as the number of outputs given in the actual data. And you should notice that ideally both should be having the same output, because clustering also tells us works in a similar direction, right? Because when we are classifying something, the classification would have done or the original data based on some similarity between the records, right? So something like that, that is what we are doing on clustering analysis. So for example, if you see some of the features for x1, x2 and x3, and you have some torque value, speed value, number of the design of the brake, something so on, and then based on that in the original output you might be having that as a BMW, then and the other record might be having Porsche, and the other record might be having say Alto. Now when you do the clustering analysis, it's quite logical that all the records with BMW should have some similarity, all the records with Porsche should have some similarity, all the records with Alto should have some similarity, and then you will come up with different clusters. Once you get different clusters, this you have to check whether, of course, the original output would be better in comparison to a clustering. But then when you do predictive analytics, like once you have this data, complete data set, now just do the predictive analytics or the classifier algorithm, implement the classifier algorithm, assuming this is as your original y in the first case, and in the second case use this as your original output, and then perform the classifier algorithm for any one test record, and then identify this predictive modeling is working, this classifier algorithm is working good on actual output or on clustered output, what we are getting. So this would be the final project, and this would take a lot of efforts from you guys. It's not very straightforward. So as In the first method, this would be considered as your y output as a target variable, and then you will do the predictive analytics. You will do complete training and test analysis, what we do, split the data and do all the analysis, and then try to predict for any one test record what would be the y output from the test data set, and just try to compare this y predicted output value with y actual output in your given data set. Now, in the second method, remove this feature from your analysis. Consider this as your new actual outputs, the cluster numbers. Okay, by now, when you do clustering analysis, you would know that we have taken only 3 clusters, and then you would easily be able to identify one signifies what, whether it is BMW or Porsche or Alto. 2 signifies what. So when you do analysis, you will come to know what data set does 1 have, what data set 2 has, and what kind of data set does 3 have, right? And then you have to read that data and you have to analyze. It's quite logical when you have very high price that belongs to Porsche, and then quite high mileage might go with Alto, something like that. And then you have to neglect this, as I told, and then consider this as your actual outputs, and then do the same predictive analytics. And now compare your predicted output with this Y clustered output. And notice this predicted output or the classified output matches well with whether the actual output which was there in the original data set, or whether it matches quite well with the clustered output. Okay, cool. So that was the thing which I had, and start with a new topic, which is principal component analysis. And this is very interesting. Try to understand this. It will be useful, and a lot of people will ask you this question in your interview also. So what is this principal component analysis in first place? We have to understand that this is not a classifier algorithm. This is neither classifier nor predictive algorithm, or like this is neither classifier nor regression algorithm. So what it does is, suppose you have in real life, you can have n number of input features, right? For example, say you have 500 input features. Then how would you tackle with this 500 input features? And how would you say that these 5 input features are really significant in terms of determining your output? Are they really influencing your output in predicting your output? No, maybe yes, maybe no. And if it is no, then we have to make sure that we have to reduce the number of features, because if we have 500 features, then what we are doing is we are making our computational quite slow. And as we all are mechanical engineers, we know what does computation means. Computation in the sense, when you run any simulation in your mechanical projects, you must have noticed that if you have the mesh quite high, if you have a large number of meshes, or if you have number of cells quite high, then the simulation time would be quite high. Or if the physics is quite complicated, then the computational time would be quite high. Simple. Similarly, in maths or in machine learning, if you have high number of features, then the computational time would be quite high. It's quite natural, right? Just imagine that you have a matrix of say 3 by 3 and you have a matrix of 10 by 10. And say you want to multiply this 3 by 3 matrix with 3 by 3, let's say, and then 10 by 10 matrix with 10 by 10. Straightforward, that 10 by 10 matrix would take a lot of time, right? Similarly, when we have high number of features, it will take a lot of time. And of course, if you have the good amount of domain knowledge, then you would be able to find out what features are significant in terms of determining your output and what features are insignificant. Or you can do some lot of exploratory data analysis and try to find out if there is any multicollinearity problem. Then you can try reducing that also. Sometimes it would be really difficult when you have very high number of features and then you try to understand each feature and then identifying, then implementing the prediction model. It would be really difficult. So there is something called as principal component analysis. Okay, as the name suggests, it is an analysis which is done on the components. Okay, so what this technique does is it brings out the variation and the patterns in a data set. That means it tries to convert your original features into new features such that, so first of all, principal component analysis will not reduce your input features. That is your analysis by which you have to reduce your input features. But what principal component analysis does for you is it converts your input features into some other features. Okay. And now how does that do? That we learn in an advanced course. But here, what we need to understand is it converts all, say if you have 10 input features, it will come up with new 10 input features. Simple. That is how it works. But when it converts 10 input features into 10 new features, it makes sure that that lot of information should be carried by only 2 or 3 input features, or maybe 4 or 5 input features. So by that, what you're trying to do, for example, if you have 10 input features which have 100% of information of the data, and now once we implement principal component analysis, what it does, it will come with new 10 input features such that 3 features would have 95% of the information, and then remaining 7 converted features would have only 5% of the information about the data set. That means what you are doing here is you are trying to assume, or you're trying to do some approximation, but then you're trying to reduce your number of features for your analysis so that you can reduce the computational time. Just imagine something similar to mechanical analysis. Okay, what we do in mechanical, when we have a lot of physics and we are working with, say, conjugate heat transfer, where we have to work on both solids and fluids at the same time. As we know, if you want to solve any equations in the fluid, we have to use Navier-Stokes equation. And then if you are working on transient analysis, you have to perform Navier-Stokes equation every time on the fluids, right? So there is something called as co-simulation. If you try to explore this, because I know that most of you are mechanical engineer, that's the reason I'm giving you an analogy with respect to mechanical engineer. So now if you go with respect to mechanical engineer example, which is, say, co-simulation. In co-simulation, you segregate solids into one simulation file, fluids into one simulation file. Okay. And then you are trying to approximate. What you will do now here is you will make solids as transient and fluids as steady. So by this, you don't have to run your Navier-Stokes equation for every iteration. Okay. So what I'm trying to do here is I'm doing some approximation, assuming that my fluid would be steady and my solids would be transient, because in solid we have to just solve for energy equation. But in fluids, if you notice, we have to solve for continuity equation, and then we have to solve for all the 3 momentum equation, x, y, z, and then we have to solve for energy equation also. So it takes a lot of time if I try to solve these equations for every iteration. So now I'm segregating that. So by this, yes, I'm doing some approximation. I have to compromise with the accuracy, but then we will reduce the computational time. Okay. And also there are few other things. If you try to understand, if you try to explore, there are some more advantages of co-simulation that you can look at that you can already explore it. Okay. I don't have to explain that in this course. Anyways, for example, just say that you are working on component analysis. And for that component, you have to use complete vehicle for doing the analysis, which takes a lot of computational time, because you have to solve the simulation for all the XYZ direction. Now just assume that if you're considering the body as bulk in the sense that the parameters such as temperature and the heat transfer coefficient or some other parameters, say example, but mainly which is temperature, right? Because we always try to evaluate temperatures in our thermal simulations. So if the temperatures are not changing in XYZ direction, it's changing only with time, then we can always go with 0D analysis. And what is that? Lump capacitance method, which I've already explained in one of the previous sessions. So something like that. We have to compromise with the accuracy, but then with how much we need to compromise, that it depends on the problem definition. And then with this accuracy compromising what we are doing, how much time we are saving, that we have to check for. Okay, so it's just not that we are compromising with accuracy. We have to make sure if we are compromising with something, there has to be some advantage, right? So we have to check for the computational time, and that's the main advantage of PC. Okay, so how does it work? That's important now. Now if you see, we have an original data set here, say x and y, and let's say that rather than taking x and y, let's take this as x1 and x2. Okay, then please remember that this y is not your output feature. Okay, this is one random features which we are talking about here. To explain it to you on a graphical representation, because we always consider this as horizontal axis as x and vertical axis as y from our school days. That's the reason that representation has been taken. But please remember that this x and y here are some input features. Say two input features we are working on. Now, see, this is how your data points are represented. In this data point, if you notice, each input feature is contributing something to your this data point, right? Now, just imagine if I convert my new xy axis, instead of like this, if I convert it like this using some transformations. I'm just telling you to assume it, okay? Real mathematics will come in the advanced course. How do we do that? So if you notice now, it's quite straight here that the value for this new axis, all these data points value for this coordinate, the new coordinate would be 0. And for this new coordinate, it would be some positive values and some negative values, right? So that is how, by using some analysis of mathematical representation, using linear algebra, what we are doing, we are making sure that the variance or the variation of these data points are with only this coordinate system, but not with this coordinate system. Okay. Now, to represent that again, let's take this example and convert this into 1D diagram of x and y. Say this is x. This is, say, somewhere near 2 and 4 on this number line. This point is also somewhere near 2 and 4. This point is located between 4 and 6. This point is located between 4 and 6. This point is located at 8, near to 8. Now, take the same thing for y. Do these projections on x. Do the projections of data points on y. And you would notice that this y here, between 2 and 4, there are 2 points again. Between 4 and 6, there are 2 points again. And near to 6 and 8, near to 7, there is one more point. Right? Now, PCA, it does internal calculation of linear algebra. And then what it does, it comes up with the new input features. It converts x and y into PC1 and PC2. Okay. And then what it does, it will take this axis, which is quite simple to imagine, right? Because that's quite simple to understand here. But when it goes in multi-dimensional, it will be very difficult to analyze, okay, and to visualize. But here it's okay. That's the reason I've taken an example of two input features. So here, if you notice, now we have taken this transformation or linear algebra analysis. We have done some linear algebra and then we have come up with PC1 and PC2. And here, the same points are represented here, okay? Now, if you notice, if you project these points on PC1, the points are represented on this number line for PC1. And if you project these points on PC2, that will be projected at 0. Now, it's quite simple to understand that the variation of these data points across PC2 is almost 0. Let's say 1 or 2%. But the variation is more on PC1. So what we are trying to tell here is, rather than using this data point for our analysis, whether we are doing supervised or unsupervised, that's a different thing. Whether doing clustering or predictive modeling, that's a different story. But let's say that instead of doing your predictive model on two features, now we have converted this into new two features, and then by looking at these two input features, PC1 and PC2, it's quite straightforward that the variations in PC2 is negligible, that means the information carried by PC2 is almost negligible. But the variation in PC1 is more, so the information carried by PC1 is quite more. That means in this case, I can say that because the data was so organized with single coordinate, I was able to get all the variations. That means might be 99% of the information is carried by PC1 and 1% of information is carried by PC2 with this new PC1 and PC2 features. But if you see this original input features, you already know that both of them are actually carrying in equal amount of information, right? But by converting that into new features, PC1 and PC2, it's quite straightforward that PC2 is carrying very less amount of information. Now there could be a case, so this is important. Say this point might be lying somewhere here. Say this point might be lying somewhere here. Okay, this point is slightly above now. Let's assume this point is slightly below. Now, when you do PCA with this coordinate, now you would notice that this point will be slightly above, this point would be slightly below. Okay, and then when you project these points in X and Y, the X might be looking at here only, might be here only, but Y values will be, might go somewhere around here. This one point might go somewhere here and one point might go somewhere here. Making sense? So with this, what we are trying to tell here is, again, the information carried by PC2 might be there. It might be quite significant. Maybe instead of now, with this example, which I have taken, the new example which I have taken, it had quite a variation, but still this variation is very less in comparison to PC1. Say the variation previously, like for previous PC1 and PC2, it was 99% and 1% with this exact example, what is showing on the slide. With the new example which I have told just now, say the variation with PC1 is 95% and PC2 is 5%. So then again, it's up to us whether we have to choose PC2 or not, okay, for our analysis. If we want to come up with a model with 5% of error, then we can neglect PC2 in this second example. But if we want to be very accurate and then the error percentage would be, say, with 1%, then we have to account PC2 also in our analysis. But when we are accounting PC2 in our analysis, then the whole essence of PC1 and the PC2 is gone, because originally we have two inputs. Now again, I'm converting that into PC1 and PC2, and then I'm using PC1 and PC2. So there is no advantage, right? It's like I'm doing some extra work here. So this principal component analysis can only be used when you have very large number of features. So this is just an example which I'm trying to show you in two-dimensional. Okay. Of course, it will have some approximations, because now also if you see, these values are like very near to 0, but there are some values which are at 0.1, 0.2, right? So maybe 0.2 or 0.5% of variation of the information is being carried by PC2. Okay, so you are compromising with the accuracy, but then you are reducing the computational time.